second derivative, testing it, doing that. Say it again. No, that would be like rectilinear motion moving back and forth on a straight line. This is concavity and increasing and decreasing. We'll review what concavity is. No problem. Okay. So we have already identified how to find our critical points, correct? And we've already kind of talked about what critical points are. What are they?
Where the slope is 0.
Where the derivative equals 0 of the first derivative equals 0. It could also be where our first derivative is what?
Changing direction. Oh,
Undefined. Undefined. Okay, we did all of that before. That was when we did extrema, so our minimums and our maximums. And when we test for absolute, that's when we use our endpoints. But this is true for relative or local minimums and maximums. So we're going to review that first derivative and identifying minimums and maximums, and then move into the second derivative part of that. So this is actually technically called our first derivative test. In our first derivative test, if my derivative value is less than 0, then my function is decreasing on that interval. If, however, my derivative value is greater than 0, then it is increasing on that interval. We use that increasing and decreasing to identify where our minimums and maximums occur, if they exist for that portion of our graph. If it equals 0, that's a critical point. So that's where we test on either side of. That's not done. You're fine. So we're going to do an example because, as I said, we've already done this, so it's not going to be anything new. The example I would like to use says to use the first derivative test to determine the local extrema values of the function and identify any absolute extrema, if they exist. How do I know if I'm going to have absolute extrema?
There's like that. Or if it goes up forever.
So if there's an interval that I'm looking at it on, that's how I know if I'm going to have absolute, which tells me if I'm going to have endpoints that I have to test. So the first example I would like to use is y equals negative 2x cubed plus 6x squared minus 3. If I'm looking for extrema here, am I going to have absolute extrema or no? Liam can't answer. No, why not, Devin? There's no interval that I'm telling you to test on, so I don't have to worry about that. I'm only finding local here. So when I go to find my extrema, what do I have to do with my original function? Remember? Take the first derivative.
Bro, I got this.
So when I take the first derivative, it's just power rule. We drop the cube down. 3 times negative 2 is negative 6x. My exponent becomes a 2. On my second term, I do the same thing. Drop the 2 down. 6 times 2 becomes 12. And my exponent reduces to a 1. In order to find my extrema, I need to test at my critical points. How do I find my critical points with this derivative? Set it equal to 0 and solve. So I have 0 equals negative 6x squared plus 12x. I really don't want to have to do the quadratic formula, so I'm going to factor out a common factor and go from there.
0.
So I'm going to take out a negative 6x first, and that's going to leave me with an x minus 2. And I take each of those and I set those equal to 0. So I have negative 6x equals 0 and x minus 2 equals 0. And Liam already spoiled the fun for us. Clearly, x on this one has to equal 0 because when I divide both sides by negative 6, 0 divided by negative 6 is still 0. And I add the 2 over on this one and I get x equals 2. Is this ringing a bell? It should be. You did extrema homework over this last week. So these are my possible candidates for being a minimum or a maximum. How do I determine which one is a minimum, which one's a maximum, or if either of them are? We have to do a number line, and then I'm gonna have to plug those in eventually and find their Y values because that's helpful. So on my number line, I only care about the values 0 and 2, and then the intervals around them. I'm going to be plugging numbers into my derivative because that's how I determine increasing or decreasing.
Find the Y.
Yeah, when we get back to that. Okay, so I know at 0 and at 2 is going to be 0. So I'm going to test negative infinity to 0 first. Doesn't matter what number on that interval I pick. No, so let's pick negative 1. Let's take negative 1 and plug it into my derivative function and tell me what you're going to get. Am I going to get a positive or a negative?
Big positive.
A big positive?
By positive, I meant the
No.
number minus sign.
What's it going to be? Who thinks positive? Who thinks negative? Good. Just check in. I don't care about what kind of negative it is. I don't care if it's a really small one or a really big one. I just care that it's negative. Then I test between 0 and 2. So what's a number between 0 and 2 that I can test? 1. Awesome. Plug it in. Am I going to get a positive or a negative? Positive. Then I pick a number between 2 and infinity. Does it matter which one I pick? No. Plug it in. Am I going to get a plus or a minus? I'm going to get a negative. It is also helpful sometimes to draw the lines. So a negative indicates that I'm decreasing coming into 0. A positive indicates that I'm increasing. And then a negative again indicates that I'm decreasing. This actually helps me visualize what's happening on my graph, which makes it easier to identify what's a minimum and what's a maximum. So when I'm talking about a minimum, to the left it's going down, but to the right it's going up. So which x value is a minimum on this graph? 0. A maximum then is a hill. So from the left it's going up, but from the right it's going down. So which one of those is a maximum if it exists? 2. So without having done any other work, I identified my minimum and my maximum. What? I meant like anything else crazy. So then what I would do is I would take 0 and I would take 2 and I would plug them back into the original function to get the y values to identify the points where these occur. So when I plug 0 in, I get negative 3. When I plug 2 in, I get 5. So those y values also support that 0 is a minimum and 2 is a maximum. Well, no, this was the first derivative test.
Wait, how do you?
Yes, x is into the original. From the first derivative test, we can also identify intervals where I'm increasing and where I'm decreasing, right? It's literally just the plus or the minus. So where am I increasing on this number line? Between what two numbers?
0, 2.
0 and 2. So I would write increasing on the interval 0 to 2. Then where am I decreasing?
Negative infinity to 0.
And
2 to infinity.
okay, so I'm going to have 2. When I have that, I connect them with a u. So negative infinity to 0, u, 2 to infinity. So we always use interval notation to identify where we're increasing and where we're decreasing. Yes, because I know at the 0 and at the 2, I'm technically not moving at all. I only care about in between them. The only time I would use a hard bracket on these is if I had an endpoint that I was including at. Any questions on that? Anybody super confused by the first derivative test and what it tells us? So what?
Yeah, what it tells us.
It tells us the critical points, which helps us identify extrema, and it tells us where it's increasing and where it's decreasing. Anything else? Okay, second derivative test, which I think is just as fun. It's literally the same process, but with the second derivative. Nothing super crazy. So our second derivative test, tells me that if I get a second derivative that is less than 0, then that interval is concave down. If we can't remember what concave down is, it looks like a frown. If I get a second derivative that is positive, so greater than 0, then that interval is concave up. Up like a cup. This also connects to our, what's it called? First derivative. So if I have a concave down section, that meant that my first derivative was decreasing. If I have a concave up section, that indicates that my first derivative was increasing. So there is a relationship between that first and second derivative. Just like on our first derivative test, we had values where our derivative equals 0, and those were important points for us. We also have that on our second derivative. So when we take the second derivative of a function and we find where it equals 0, those are called our inflection points. So these are the points where my concavity changes from down to up or up to down. And it's where our second derivative equals 0 or where it's undefined. It is also important to note that not only does my second derivative have to equal 0, but I have to be able to have a tangent line at that point. So it can't be what?
So it can't be infinite slope.
Right, so like there are some restrictions to it, but yes. Present at that point. There are very few instances where I'm going to have a 0 for my second derivative where a tangent doesn't exist. And for the most part, you're not going to see that. It's just something we have to tack on there. We ready to try it out? You guys do not look thrilled at all. This is fun, right?
Did I have to ask that question?
Oh yeah, no, this class is terrible, awful, but that's okay. Example, I would like to use the concavity test to determine the intervals in which the graph of the function is concave up and concave down. So I'm looking for intervals of concavity. The first function I would like to work with is y equals negative x to the fourth plus 4x cubed minus 4x plus 1. So if I'm testing for concavity, which derivative do I need? The second. So I need to take the derivative once, and then I'll take the derivative a second time. So what is my first derivative going to equal here? Negative 4x cubed plus 12x squared minus 4. Perfect. What then will be my second derivative? Lauren can't answer. Negative 12x squared plus 24x. Anybody have any issues with taking that second derivative? Okay, if I would like to find my concavity, I first have to find my inflection point, so where that concavity changes. How do I do that? Set that second derivative equal to 0. So now I have 0 equals negative 12x squared plus 24x. Again, I could use the quadratic formula, or I could just go ahead and pull out a common factor gonna go from there. I'm gonna take a negative 12x out of both of these. And I get negative 12x times x minus 2. And I set each of those equal to 0. And I solve for x. Did everybody get 0 and 2 as my inflection points? Okay, we don't just blindly accept that those have to be inflection points. We still have to test them because sometimes it won't be. Okay, sometimes I can have the same concavity on both sides. That does happen. So in order to test it, what do you think I'm going to draw or write? A number line. Easiest way to do this. You could also do a graph, or not a graph, a chart if you wanted to, but sometimes that's extra work. So I'm testing at 0 and 2, correct?
Oh, no.
No, I'm testing around them. So negative infinity to 0, 0 to 2, and 2 to infinity. I already know at 0 and 2, I got 0 for my second derivative. So we're going to do just like we did before. I'm going to take some number between negative infinity and 0, and I'm going to plug it in to my second derivative function and identify whether I get a positive or a negative number. So let's go ahead and plug negative 1 in. And when you have an answer, tell me if it's positive or negative. Negative, right? That was pretty easy. What about, oh, I don't know, between 0 and 2, what's a really easy number to plug in? 1. So when we plug 1 in, what's going to happen? Positive. What about between 2 and infinity? Negative. Which indicates to me that this section and this section are concave down, and this section is concave up. So that's all I needed to identify for this problem. So concave up was from 0 to 2. Concave down, we had 2 of them. The first one was negative infinity to 0, and the second one was 2 to infinity. Questions, concerns, or issues with that? Anybody super confused by what's happening there?
Oh, I'm ready for that one.
Let's do a couple more examples first, but then sure.
How about one more?
One more?
Yeah.
How about 2 more?
How about 1.5?
It's gonna get worse.
No, it's not gonna get worse.
1.5. Well, you're gonna throw in.
Actually, none of those on here for right now.
On homework?
For right
On the
now.
homework either, but we're not always gonna have beautiful polynomials like that. So I wanna make sure we still know how to do it without having those gorgeous continuous functions all the time. Sometimes we will need that, yes. Say that again. I think I made 8. 4 where you find increasing and decreasing intervals, and 4 where you find concavity intervals.
So the increase decrease.
First derivative, and then concavity is second, yes. So let's do another example.
Bro, my mom's tweeting out. Yeah, my brother got a COVID test. It's negative.
We're gonna do one more after this one.
You know how in TikToks where like it shows them like with their neck broken and they're upside down? That's what it's
Okay,
I feel like I'm dead.
Oh wow.
so my function is y equals e to the x on the interval 0 to 2 pi. I know we're all super excited. I would like to find my intervals of concavity, so which derivative do I need? The second, but to get the second, I first have to take the first one. So what is the derivative of e to the x? Oh boy, that was easy. Then what's the derivative again of e to the x? E to the x. So my second derivative is e to the x. What do I do with that e to the x second derivative? Set it equal to 0. And I solve for what x value makes that 0. Is there one? E to the 1 would just be e.
E to the 0.
Would be 1. Anything to the 0 power is 1. Is there anything that's ever going to make that equal 0? No, because I'd have to have a 0 in the base and that can't happen. So there are no x values where that is true.
LX, well,
This is grand.
Yes,
Didn't you say E? One time you said it was like 2 points.
It's like 2.718 or 81.
So it's just a number.
Yeah, it's just a number. Just like pi, we use the pi symbol, but pi is still just a number.
It's weird.
It's just an irrational number. But it's a very common one that has a special relationship with logs, so they put something with it. Okay,
Oh, well,
so there are no inflection points, which means I still have to identify the concavity on this interval, but do I expect the concavity to change in there anywhere?
No.
No, because I had no inflection point, so it's all gonna be the same.
Every
So I just have to pick one number between 0 and 2 pi. That's all I have to do.
forward.
put a good old line.
I would do 1. That's so much easier. So what's e to the 1?
2.718.
Is that positive or negative?
Positive.
So it's positive on that entire interval, which means that entire interval is concave up.
That entire function.
Well, yes, but that's beside the point. Ah,
Is it negative one to infinity?
no, because I was given an interval, so I can only be concave on that interval. Yes, when we're given an interval, we use the hard brackets. If we're not, we assume it's negative infinity to infinity, and we would use soft brackets.
Oh, yeah.
Okay, so like if there's not infinity.
Yes.
All right, I'm done.
Okay, questions, concerns, or issues with that? We are gonna do one more.
Yeah.
Basically,
Now I just want word. Same.
Liam's got notes in his brain.
He's got notes in his brain.
You get it?
Hey, this is one thing. That's my favorite.
How does Liam know everything?
From freaking Algebra 2 Apex.
You just,
Yeah.
You just sit around and
They
watch
do a lot of
Khan
this fun
Academy.
stuff. Okay, let's do one.
Literally.
Tim
No
whipped out,
joke.
Tim whipped out some calculus book and anatomy. And I was
Yeah,
like,
he was like working on it.
I was like,
bro,
what are you doing? He said, math. I said,
I wish I had that dedication.
I was like, what are you doing?
I barely do my math.
Well, I mean, he
Yeah,
enjoys it.
we've got
Obviously,
some book.
so it's not like he's like suffering that much. So.
You hate that function?
I do a lot.
Why do you hate
Can't
that?
the X's just cancel out? It's like
No.
0.
No, because there's no x with the 1, so that can't happen.
Huh?
Nothing.
It has to have like.
It has to be present in all terms.
Yeah.
What did you say?
I just know, but it's getting after that, now you're just getting offensive.
Okay, kiddos.
We just forget about
I would like to identify the intervals of concavity. So what do I need to do?
Second derivative.
Second derivative, which means I first have to find the first one.
Good old quotient rule.
Oh, good. I love quotient rule.
Yeah.
So when we do this, let's make sure we remember how to do it. So we're going to talk our way through it. I take the derivative of the numerator, which is 1, times the original denominator, which is x plus 1, minus the original numerator x, times the derivative of my denominator. What's the derivative of x plus 1? 1. And then all of that over my denominator squared. From here, I just go ahead and simplify it out a little bit. Distribute the 1. I get x plus 1 minus x over x plus 1 squared. The x's are going to cancel, and I just get 1 over x plus 1 squared, which I can easily rewrite as x plus 1 to the negative 2 power. So my first derivative is x plus 1 to the negative 2 power. By writing it like this, I set up to do chain rule for my second derivative instead of quotient rule again. Oh, goody. So we can talk our way through that
Oh,
one.
wait, it's negative 2, x plus 1, so then negative 3,
Times
the inside.
derivative of the inside.
Oh,
Which
that's
is
what
just
I meant. That's what I meant.
So chain rule, I dropped the exponent out front, so the negative 2 dropped out front, the inside stayed the same. I decreased my exponent by 1, and then I multiplied by the derivative of the inside, which I could just say is negative 2 times x plus 1 to the negative 3. Of course, we like to simplify this, so I would make this negative 2 over x plus 1 to the positive 3, just to make it a little bit nicer to look at. What do I do next?
Set it equal to 0.
I set it equal to 0 and I solve. I have a question for you.
Multiply that.
What kind of question?
Is there any x value that I could plug into this that's gonna make it equal 0?
No.
No, because I'd have to have a 0 in my numerator, and there's no variable there, so I don't have to worry about it. But I don't just test where my second derivative equals 0, right? I also test
Undefined.
where it's undefined. Is there any x value I could plug in that would make that undefined? -1 because it makes my denominator equal 0. So what I have to do next, because it made my second derivative undefined, I have to make sure it doesn't make my original function undefined, because if it does, I can't use it. So then I take that -1 and I plug it back into my original function, and what happens? It's undefined, which means I have no inflection points on this entire thing. Which means that I assume that my concavity stays the same on the entire interval. So what can I plug in? Literally anything except -1.
A little 1 in there.
Okay, so what happens when I put 1 in there?
You get 1/2.
What did we put it into?
Never. Which was obviously wrong.
Right, we want concavity, so I want second derivative. What happens when I plug 1 into that second derivative? Which is,
I put 1, so 2.
okay, what happens when I plug 1 into that second derivative? What does my denominator go to?
-2. Oh wait, what?
What happens when I plug 1 in for that x? I get 1 plus 1, which is,
Oh,
2.
and then 2 cubed is,
8.
and then -2 divided by 8 is,
-4.
which means my concavity is what?
Neg-
Down, concave down for that entire thing. Because I had no inflection points. I'm a little bit concerned now.
No, it's, wait, I
-4 makes it concave.
because it's negative.
Because it's a negative number. It doesn't matter what it is, just that it's negative.
You know what?
All I care
And
about.
It's concave down at, is it -3? Is it no-
We assume it's on the entire thing.
Do you have to?
Although it really doesn't matter.
We're not
Would you
gonna
say
write that.
Would you want to write a union excluding -1?
Yes, you would want to do that. In theory, because it's undefined.
I'm confused. Wait,
So we would say concave down. On my entire interval, except -1. Because -1, it was undefined.
Yeah, but you're telling me there's no other number that
Can you think of another one that makes
I don't know.
x plus 1 go to 0?
No.
Because I can't. Okay, so then you're not gonna have one like this, I don't think, on your homework. They're all pretty much the basic ones just to get you in the practice of doing it. And then after Christmas break, when we revisit this, we're gonna kind of put it all together.
Okay.
But I think you guys need a break, and I really wanna get through optimization before Christmas.
So this won't be on our phone?
This, no, I do not want, I'm not kidding. Well, the ideas on your homework, one like this is not. Okay, so homework's on Canvas, it is due tomorrow.
Alright. Are you like staring at me all the time? You stop.